Okay, so let's just take a minute and talk about what the difference between a one and two-sided alternative is. So the alternative hypothesis is one-sided if it states the perimeter is larger than the null or if the perimeter is smaller than the null. That's basically like saying, let's say that the proportion is, we're believing that the proportion of people that kiss on the right is equal to 50%, but we believe that it's more than 50% or less than 50%. It's one-sided because I'm only checking to see if it's more than 50% or less than 50%. A two-sided test states if the parameter is different from the null. So what that means is if we say, hey, if the null is that people equal 50% of the people kiss on the right, if it's two-sided, that's like saying, oh, wait a second, okay, we're not sure if more than 50% of the people kiss on the right or less than 50% of the people kiss on the right. So we're just going to state not equal to. So the two-sided states that they're basically different. We don't know which direction they're different in. They're just different from the null in some sort of case. Remember that the hypothesis always refers to the population, not the sample. Be sure to always state the null and alternative in terms of the population parameters. It's never correct to write a hypothesis about your sample statistic p hat or x bar. And the reason for that is you come up with the null and alternative hypothesis before you even take a sample. So statisticians and scientists and researchers, they always come up with a null and alternative before they take the sample. They do not base the null and alternative off of the sample. They make the claim and then make the alternative and then take a sample to see if their alternative is true. So just be really careful with that. All right, so let's just take a look at what exactly a one-sided versus a two-sided test look like. So we said a one-sided test is if the mean is greater than 0. So we're just taking a look at means now. Or let's say the mean is less than 0. Those are one-sided hypothesis because we're only looking in one direction, greater than or less than. If our value greater than the parameter, we're checking to see is our value greater than the parameter or is our value less than the parameter. So basically what this is saying is we're testing to see if our parameter is somewhere in here, is it bigger than the parameter or is it smaller than the parameter? So we're basically checking the tails of the normal curve. Two-sided, notice how this says mean not equal to 0. I'm just choosing a number 0. It's two-sided. It's saying, hey, we don't know if the mean is greater than 0 or less than 0. We just think that maybe it's different than 0. So that's a two-sided test. We're checking in both directions. We're checking to see if our claim is potentially greater than or less than the hypothesis. So that means on our normal curve, we are checking to see, we're finding probabilities in the tail above and the tail below. And we'll be going over more what this means in upcoming sections. Okay, so how do I know whether or not to use a one-sided or a two-sided hypothesis test? So just what I said before, hypotheses are formed before the data is collected. So the researcher, the scientists, the whatever, they always decide what their null and alternative hypothesis are going to be before they even collect their sample mean or sample proportion. So when you're doing this, use the wording of the question to guide you. Don't use the data. So in the question, it will state, is it different than the mean? Is it less than the mean? Is it greater than the mean? So you would look for the words changed, different than. Those are all indicators of a two-sided test. Basically, if it doesn't say greater than or less than, it's going to be a two-sided test. Okay, so what are some common mistakes when we're writing the null and alternative hypothesis? Always make sure you use the parameters and not the statistics, okay? It's always in terms of the population, not the statistics that you're using. The statistics that you're using, we're just using to test against the population, all right? So that's why we don't write the null and alternative in terms of the population. You're always going to write it in terms of the parameter mu and p, so don't ever use x bar or p hat. Okay, all right, so let's just get some practice writing some null and alternative hypotheses. A researcher is interested in whether alcohol consumed by pregnant mice can affect the birth weights of their offspring. It's known that for untreated mice, the birth weights of newborn pups are normally distributed with a mean of 200 milligrams, okay? So we want to read this very carefully. we want to know if it can affect the birth weights of the offspring. Since we're checking to see if it can affect the birth weights, it's not saying are the birth weights higher or the birth weights lower. It's just saying, oh, we don't know if they're higher or lower. Therefore, that's going to be a two-sided test. All right, so the null is assuming that it's not any different than what the population claim is. The mu is equal to 200. The alternative is based on the wording of the question up here. And then make sure that you define what mu is, the birth weight of milligrams of mice. Now notice how this says not equal to. So that's like saying we don't know if when you take alcohol, if it's going to be greater, is it going to make the newborn pups weigh more, or is it going to make them weigh less? All right, so let's take a look at the second one. As a group, final exam scores are normally distributed with a mean of 42. The instructor tries a new method and believes the scores will be affected. All right, so read this carefully, and we know that this is the population. She believes the scores will be affected, but she doesn't know if it's greater than, if it's going to make the scores better or if it's going to make the scores worse. So our null is always assuming that there is no difference, that the new method of instruction is not going to be any different, so therefore the mean holds true. That's the null. The alternative is going to be not equal to, because we don't know if the scores are going to be higher or if they're going to be lower. And then notice how the mu is defined. Okay. Take a look at the third one. It's known that under regular circumstances, rats in a study can eat an average of 10 grams of food each day. A test drug is administered to rats. The expected result of the drug is to reduce food consumption. All right, so this is going to be one-sided since we're looking reduce food consumption. So we want to see if it decreases, so that's going to be less than. Now also notice that we're making the null an alternative before they actually run the experiment, okay? So they're not using the experiment to then come up with a null and alternative. They're coming up with a null and alternative, then running the experiment, and then checking to see if their claim was true. Okay, so the mean is that, okay, wait a second, that the drug doesn't change it, so the weight is still going to, or they're still going to eat 10 grams a day, all right, and then the alternative is that it's less than 10 grams because we're checking to see if the drug reduces food consumption. Notice how mu is defined is the amount of grams eaten by rats. All right, so Okay, so this is just a quick activity for you to test a claim to see whether or not, just to sort of see how significance tests actually work. So what you're going to do is, if you could just take a minute and complete this activity, you're going to go to this website, launch the applet. On the next slide is your set of directions. Basically what we're going to do is we're going to take a look at a claim made by a basketball player. We're going to use a simulation to see if the claim made by the basketball player is actually true or could possibly be true. All right, so a basketball player claims to make 80% of the free throws that he attempts. We actually think that he's exaggerating. So to test this claim, we'll ask him to shoot some free throws virtually on this website. Now notice, okay, so this is the claim. We think he's exaggerating, so the alternative is going to be less than, all right, and we're coming up with the null and alternative before we actually do the experiment. Then we're going to do the experiment or the simulation to test to see whether or not he's exaggerating. Okay, so you're going to launch the applet, set the applet to take 25 shots, click shoot, and record how many of the 25 shots the player makes. Click shoot again for 25 more shots. Repeat until you're convinced either that the player makes less than 80% of his shots or that the player's claim is true and he makes about 80% of the shots. Just go ahead and try that. Okay, and then click show the true probability and just determine whether or not you were correct in stating that he actually made 80% of the shots or he made less than 80% of the shots. All right, so let's just take a look at how we would do this test for our basketball example. All right, so number one, we're coming up with the null and alternative hypothesis, okay? All right, so for the basketball example, we said that the claim, notice how it's in terms of population proportion, is no different. We're saying, all right, you're pretty good. Okay, the null is that it's not any different. It's actually 80%. But the alternative says, I actually think you're exaggerating. We actually think that you make less than 80%. Notice how P is defined, the proportion of free throw shots made. So to test our basketball player's claim, we use the applet to attempt 50 free throw shots. In the simulation, he makes 32 of them. Okay, so his sample proportion that he made of the shots based on the simulation was 64%. What can we conclude about the claim based on this sample data? All right, so we can't just look at the 32 out of 50 and say, oh, okay, that's actually less than 80. Yeah, we're good to go. Okay, sure. The probability is he actually doesn't really make 80%. No, we can't just quite do that. We have to find the probability that this is going to occur. So sort of think about that as like a confidence interval. If we were to create a confidence interval, would that confidence interval get the true proportion, all right, or would it not lie in the confidence interval? Because remember that this is just one sample. If I did this another time, would it be 64 or would it be 80? If I did this again, would it be 30 or would it be 75? Okay, so this is just one sample proportion of him making the shots. So I want to find the probability that this occurs. Okay, so if this probability occurs, if this proportion occurs pretty often, all right, then his claim is probably true. All right, so what can we conclude? So based on the evidence, we might conclude that his claim is incorrect. But we use software to simulate 400 sets of 50 shots, assuming that the player really is an 80% shooter. So you can say how strong the evidence against the player's claim is by giving the probability that he would make as few as 32 out of the 50 free throws if he makes it 80% in the long run. Okay, so that's kind of confusing the way that's worded. Okay, so let's think about this. All right, so here's his 400 shots, okay? In 400 sets of 50 shots, there were only 3 times when our shooter made as few as the observed claim as 0.64, okay? So based on our simulation, so if I were to take this, if I did 3 out of 400, okay, that means only 0.7% of the time was he going to make a proportion of 0.64, around that area, okay? Now, the observed statistic is so unlikely, okay, so this is not very likely, that if the actual parameter is 80%, then it gives convincing evidence that the player's claim is not true. So we're assuming that the player's claim is true. So if the player's claim is in fact true, that means when I did this experiment or when I did the run, he should have made it closer to 80% of the time. But since he didn't make it close to 80% of the time, and if he really did make it 80% of the time, this should only happen, it's the probability of this occurring is very, very low. And since the probability that it's occurring is very, very low and it still occurred, that gives us evidence that his claim is incorrect. Okay, so in reality, there are basically like 2 explanations for the fact that he only made 64% of his free throws in the example that we had. Okay, so number 1, the null hypothesis is correct. All right, so hey, maybe we just got an unlucky sample. The player's claim is correct. He does in fact make 80% of his shots, and just by chance this very unlikely outcome occurred. So this is like him just having a bad day. So he actually does make 80% of the shots, but hey, today he had a really bad day and just by chance alone, we got that result, okay? The other idea is that the alternative hypothesis is correct. The population proportion is actually less than 80%, so the sample result is not an unlikely outcome. If the population proportion is actually less than 80%, then him getting this 64%, that's probably actually pretty common. The basic idea here is that an outcome would rarely happen if the null hypothesis were true. Okay, so assuming that he makes 80% of his free throw shots, that's like a tongue twister for me, if that Okay, sorry, this is confusing wording. An outcome that would rarely happen if the null were true. So in this case, this outcome is only going to happen 0.7% of the time. So if the null were true, this gives us good evidence that the null hypothesis is not true. So we are assuming that he makes 80% of his shots, but then when we get evidence that he doesn't make 80% of the shots, that's not going to happen very often. Given the fact that he makes 80% of his shots, then we're assuming that the null hypothesis is not true.